Welcome to my talk on using context role-oriented programming for swarms to alleviate the micro-macro problem here at SEAMS 26 in Rio de Janeiro, Brazil. In this talk, we are looking into swarms, basically the central idea from nature that many individuals organize themselves. And of course, there are many definitions out there. We are using this one here by Dorigo and colleagues, where we basically say robot swarm is a self-organized group of at least 3 robots which cooperatively solve a problem using only local interaction and have emergent and collective behavior. In our case, it's very important to make a difference between the macro and the micro scale in terms of the interactions between the individual robots. The central idea here is basically that you can actually only program on the micro scale. That is, you can only program an individual robot, um, but you cannot program the swarm, which would be on macro scale. And the problem for the developer is always that if he is programming on micro scale, he has to predict actually the behavior on macro scale. And yeah, we actually aim to alleviate this problem. We want to help the developer to get a macro perspective while doing micro programming. That is our goal of the paper. And we tried to do this by actually using context role-oriented programming, which is an extension of the central idea of object-oriented programming. Basically, you see the small example here, which is a class diagram extended with a compartment with a context, which includes roles. And the idea is that objects, so instances of classes, can play roles to actually change the behavior and state of the object. And only while these roles are being played, the change behavior actually occurs. And if the object stops to play the role, then the change behavior is also stopped again. We actually have an implementation for a programming language called Context.jl, which allows to implement using roles. So it's basically an extension to the object-oriented paradigm. And we, of course, used this language to implement our swarm approach, which I will now present in the following. In general, what we aim to do is we want to alleviate this micro-macro problem of the software developer, and by this actually also want to help in terms of program comprehensibility for the developer, because it's hard to actually comprehend the overall program if he can't see the macro vision of his program. And we also want to improve on program explainability for the user of the swarm, for which we will actually provide a dashboard to the user of the swarm application, which gives an overview and helps to explain why certain decisions are made and others are not. So that is basically our goal. And to investigate this, we used a quite complex example scenario, which we implemented, namely a so-called foraging chain or transport chain. In this example, you see here 2 robots, R1 and R2, with a field of view. And the goal of these 2 robots is now to find the prey, to load the prey and bring it to the nest. But they shouldn't do this individually, but instead they should form a transport chain. That is, when they meet, they should actually hand over, if they have something loaded, to the next one, and this way form this chain. Now, the progress this works is basically that in the beginning, both robots actually just roam around, search for the prey. Yeah, because we don't have any swarm perspective here. Each robot only has its local program running on it. Yeah, so, and in this example here, robot 1 detects the prey, so it actually will go to the prey and load it up. Robot 2 is still searching for the prey. Yeah, he also doesn't know about Robot 1 having found the prey. It's simply searching around. Now, at some point in time, if we are lucky, actually, both robots will meet. They will get into each other's proximity. And if they do so, then they can detect actually using their sensors that the other robot has actually the prey loaded. And this basically means that they can now switch to the next mode, which says, okay, let's make a transfer point, which they negotiate among each other, and let's meet there, and then robot 1 will hand over the prey to robot 2, which then can continue basically to go to the nest. And this then basically would form this very simple example scenario here, this very simple chain where robot 1 is always migrating between the prey and the transfer point, and robot 2 also migrates between the transfer point and the nest. To realize all this, we have one central idea, and this central idea is shown here. It is basically taking a double feedback loop. It takes a loop on the bottom side, on the micro level, which is basically saying, okay, each individual robot needs a so-called runtime model, so basically an abstraction of its own state and what it actually perceives, in order to be being able to adaptively react to changes in the environment. Yeah, so this so-called single robot loop we have here on the micro level is basically responsible to enable the robot to drive to a certain location, to pick up something, and yeah, do these things which have no idea about the overall swarm task. Yeah. So for this, we have this robot runtime model, which is based on a single robot meta model. But then we say we want to extend this micro level with a macro level, which is also running on each individual robot with a so-called swarm element loop, which has a so-called swarm runtime model, which is based on a meta model using the compartment role object model, which is basically using roles. Yeah, so compartment role object model is CROM. And this basically says that each robot has its own idea of the swarm's state. Yeah, so this swarm runtime model is the local perspective of each robot on the current state of the swarm. So it knows about its own state and all the robots it perceived and all the elements in the environment it perceived for the task, but only on this local perspective. Yeah, so there is no global view, of course, but still having the swarm element loop actually allows the developer to basically much easier specify the overall swarm logic. Yeah, because now you can define your adaptation rules based on the swarm logic and not only on the individual logic. Now, this is basically the central idea, yeah, having this two-level feedback loop, having a swarm element loop on top of a single robot loop. And now, of course, we evaluated our approach. And for program explainability, we provide basically this nice dashboard to the user where the user can actually see in a tabular view using a web browser the aggregated knowledge about the overall swarm. This does not breach the idea of having individual robots. Yeah, it's just a dashboard collecting all the information about all the swarm elements, but it doesn't decide anything. Yeah, it's just showing the data. And here you basically see now for 4 robots, FB1, 2, 3, and 0, what is their current state, where they actually want to drive to currently, and you also see the swarm state. So you see whether they are currently playing a head role, a tail role, an intermediate role, or a joint chain member role. Yeah, so you basically can see that FB1, 2, and 3 are already in the chain team, so they basically are already in a chain, where FP1 is basically the head, FP2 is the tail, and FP3 is an intermediate. And you can also see that FP0 is about to join that chain. So he's in the join chain team and also in the chain team to become yet another intermediate robot in that thing. In terms of the performance of our approach, we basically measured the individual components we have. So we measured the single robot loop, the swarm element loop, and also the messages component, which is responsible to process actually all the incoming sensor data. We measured this for 700 seconds using an example scenario with 14 robots, which should form a chain. And what you see basically is that the messages component and the single robot loop, they are super fast, so they're much below 100 milliseconds, so no problem to see here at all. The swarm element loop is below typically 200 milliseconds. The median is around 46, 47 milliseconds. So assuming that we actually want to be able to react to something in the range of 100 to 200 milliseconds, everything is fine. Yeah. And the outliers you see here, they are due to different circumstances, which you can read in the paper. So, in conclusion, our goal was to alleviate the micro-macro problem of swarm programming. So we wanted to enable the developer of swarm programs for a single robot that he actually can take the macro perspective while programming, so he can actually easier program such swarm programs. And our solution is basically to take a double feedback loop, which is a swarm element loop with a single robot loop, and to have two interconnected runtime models. So following the models at runtime paradigm, having a swarm element loop meta model, runtime model, and a single robot runtime model. Yeah. So this is the central idea, which we implemented using context role-oriented programming, using context.jl, and we also showed that we can improve on explainability using a nice web app. That's it. Thank you for your attention and goodbye.